Thank you very much, Ricardo. I will be slightly complementary to Pierre's talk, where he's looking at the thermal aspects and looking at, Pierre mentioned WUPA and his studies as well. So we've taken assumptions with some thermal temperature frames, as it were. So the building should be well behaved from what I will look at. Educational environment. Classroom should be well behaved from a thermal point of view. And then I want to see how well can we make the building behave from an acoustic point of view. So that's what I'm looking at. There's a lot of single numbers in standardization. There's a lot of single numbers, I think it looks like, in the thermal side as well. So just to say a temperature is maybe dangerous ground as well. But it's the same in acoustics, and I think a lot of you know with acoustics that reverberation time, reverberance, the time it takes the sound to decay by 60 decibels is used a lot. It's a single number in many standards, and it's often used on one mid-frequency point. So I'd like to look at that in a much broader aspect. And from an acoustic perspective, look at to bring you those who are not involved with acoustics so much. If we think in terms of an orchestra, we need to hear the strings, but we need a balance of the wind instruments, the brass, and the percussion. It's no use if the percussion and brass drowns out everything else. Then you lose the quality of the strings. So we'll look at that, how we have perhaps a similar scenario. And when I'm looking at educational environments, of course it's teachers, it's students. I'm talking about speech communication. How can we optimize for speech communication? And I'd like you to hold this picture of the outdoor environment, the natural outdoor environment, in your heads throughout what we talk about, where the sound passes you once, and then the horizontal field is scattered and diffused in the forest, and it disappears into the sky above you. So that's an interesting concept which we can hold and see how that holds when we come indoors. So overview on how important speech communication is for teaching and learning. Look at some traditional ceilings, traditional schools, as it were, with full coverage ceilings. And then tabs, what we're really here to talk about today, when we don't have the benefit of having this full ceiling. How comfortable and how well behaved can the acoustic space be for learning? And particularly balancing the frequencies. And then look forward to, I think, what most of you will be waiting for when you had, those of you who had the opportunity to visit our Solaris lab this morning. I'll look at some measurements and results that we've had from there in a classroom setup. So if we look at speech communication, we have a speaker voice, somebody transmitting like myself, many listeners like yourselves. You're all still with me, hopefully. And what is transmitted to what is received is not necessarily actually what's coming from the spoken voice, particularly when we come indoors. Outdoors, it's more or less pretty good. But indoors, it depends on the room dynamics. And this is where we can have quite an imbalance, and that's something that we really need to look at. So I'll come on to that. But so what is spoken and what is heard is not necessarily the same, and then how comfortable we are with that. Again, down to room behavior, building behavior. So what's going on with fundamentals of teaching and learning when it comes to speech? Well, we have to hear the speech clearly. Then hopefully we can actually understand what is said. And if that is the case, we have a better chance to remember. The better or worse the acoustic environment, the more chance we have of actually remembering what's being said, even after what we've actually heard. So once we've got that in place, then we have an opportunity to focus and concentrate and actually apply what we have understood, what we can remember, and be able to apply that. So hopefully you can apply some of what you hear today. If we look at the speech and hearing, this is the whole hearing threshold. Here you see here. And our ears are developed very well for outdoors. We hear very well in the horizontal field. And speech is in this zone. We have a speech banana, as it's called. You can maybe guess why. And what we have here, when we talk in syllables and then words and sentences, what you're actually hearing are a mixture of consonants and vowels. And when it comes to speech, the vowels are a bit of a challenge. I had man flu a few weeks ago, so I'm a little bit more gruff than normal. So I apologize that the vowels are maybe carrying a little bit more energy than normal. I see some of you nodding there. You've had man flu recently too. It's quite serious. But the consonants which we need there's a danger they're masked. And this is in a perfect situation, almost in a studio situation, that this is the way speech is. So we really have to take that in mind when we go into the building conditions. If I just put this in a bit more depth, we have in the speaker system, the consonants, that's what we need. And that's a little bit like the tweeters in a stereo system, music system. And it's the consonants that give us the information. We really have to hear these to clearly hear. I hope you can hear my consonants at the back, Hyllinge. Can you hear my consonants? Pierre, thank you. Yes, good, good. But they don't have so much energy. And this is where the energy of the vowels, as we saw, which is higher, there is a danger that they will mask what's going on. They have the energy, but they don't have so much information. So this is something that we need to take in mind, because there is a potential imbalance once we go and change from full ceilings to opening up for thermal mass, and we have to really consider this very carefully. So there's a study done, and this is looking at from no acoustic treatment to full acoustic treatment in the UK a few years ago, the Essex study, and it was really looking at optimizing for hearing impaired, but they found that when they optimized for hearing impaired, they really gave very good acoustic conditions for everyone. And I'll try and explain what happened. They started off with a control room, which was no acoustic treatment at all. And actually, when you're there with the teacher, he has to come very far forward, and he can only speak like this, very, very slowly. And it's really hard to listen, and it's very hard to speak. When he had the room with a minimum treatment to meet the minimum standards in secondary schools in the UK on mid-frequencies, it was also not so easy to hear what was being said. It was a bit of a strain on the voice, and as a teacher there said, it actually is not fit for purpose for modern teaching and learning for group work, for example. You really have to work hard to listen to one person speaking, and it's not suitable when you break up from there. When they increased the acoustic treatment to much higher levels of absorption to meet hearing impairment for mid-frequency, they were able to start experimenting with group work. So it was quite a fundamental difference. And then when they increased the acoustic treatment to match across all the frequencies, they started to change the dynamic altogether. Again, it accelerated the dynamic when it was much better, lower sound levels and much better speech. And there were hearing impaired children who had to sit at the front, who in the best example could actually choose to sit at the back. So it was very good for speech and listening. And if we look how it was perceived, subjectively, the blue is the no acoustic treatment, red is the first lot of acoustic treatment, and increasing yellow and green to the highest level. And you can see this is minimizing the perceived negatives. So for example, it became less booming, less low frequency in sound. It was better for speech and better for listening, the better they got this. So this is when we're talking about full ceilings scenario. So reducing the detrimental negative effects. If we look at also from the sound levels, and then we say, well, what's the quality of speech going on? If we look at the top line here is looking at the predominantly the teacher's speech, the LAEQ, which is predominantly the teacher's speech, and then the L90 is predominantly the background ambient sounds, but also the children's speech. The signal to noise level, 8 decibels, is not so great there. If you're looking for 15 decibels really ideally, and you have that with the better acoustic treatment. But if I could try and give you an example, I should get some water soon. It's that man flu coming back. Trying to speak at that level with 8 decibels headroom, as it were, you have to speak in a very monotonic way, and it's almost like a lecture. It becomes very dictatorial, and it's very difficult to tell a story. You just have to keep it up at that flat level, and I don't think that's so interesting for you listening. However, if you can speak in this zone, you can explain that the little mouse went across the corridor and the door banged. And it's more storytelling. But it's hard to tell that the little mouse went along the corridor and then the door banged. I was banging when it's very hard to be storytelling. And this is the response you get from teachers. They engage the class much more when they can be in this storytelling mode. And then you encourage the students to talk much more as well. So it's win-win. So this is something we need to be very careful about. We need to consider the room dimensions as well and what's going on with the surfaces. We need to look at the people. How old are they? What are their sensitivities? Are they non-native speakers? Have they got hearing impairments? What's going on? ADHD. And then the activities. It's not just about lectures anymore, it's much more engaged communication, talking in pairs and talking in groups of 4 or 6. So we have to balance this. Strings mustn't be drowned out by the percussion and bass. So we have to look at the sound levels, the strength, sound strength, speech clarity. We have to hear what's being said. And of course the reverberance, but we need to look at the reverberance in the low frequency so we can avoid some booming. These can be measured in objective measurements, which is a relief as well, because when you see subjective comments, you need to be able to find ways of measuring this so we can make sure that we can achieve this. So we'll have a look at this again, but before, just to take you back outdoors, forest, sound going past your ears once, not coming back with any late unwanted reflections, no unwanted noise. And it should work very well as a concept. So what does that mean in reality? Well, I put in a little concrete, perhaps not enough concrete to give you thermal mass, but just an indication. And for speech in the classroom, what are we trying to do? Well, actually, we want to just introduce an acoustic sky. Poof, take the sound away, bring the sound levels down, and then reduce with an acoustic forest the late reflections and scatter and diffuse. And what's scattered and diffused on the trees actually ends up being speech frequencies, the higher frequencies, which is reinforcing speech, and the low frequencies disappear. So you reduce the booming effect. So that's a benefit. You get a full ceiling and then additional low frequency absorption to reduce the low frequency booming. And when it comes to the walls, actually shelving, books, good, or absorption behind to take away the late horizontal reflections. And actually also it can be good to have some immediately above. If somebody is going to stand in one position to address the whole class, then some feedback is good for perceive for the speaker. Now we have a challenge because we're going to look at tabs, and everything changes, as we can imagine, because we have to expose the structural soffit, the thermal mass, and we need convection and radiation to regulate the temperature. So we're up against it now a little bit. And unfortunately, as you can see, our acoustic sky is compromised. It is going to bring the sound levels down, but we'll have a look at some numbers. But what we lose and what's happening is, if you imagine a thunderstorm, this low frequency is coming through and is going to give you an imbalance. So now we have a classroom that's not necessarily going to behave very well. So then we have to really focus on low frequencies. Thank you. The acoustic forest is going to do something here, but it's a limited square meterage compared to what you can have above. So the bit you've been waiting for, measurements, those of you there this morning, untreated to treated rafts, and quickly run through the configurations. Acoustic rafts, as you see here, with no wall treatment at first, and then we have acoustic raft, and in red is the low frequency absorption. You can see the base pads here, and then a wall absorber, and then acoustic rafts with the low frequency again, and then applying low frequency absorption behind the wall absorbers as well. So, numbers. If you look at mid-frequency, a single number, you may think you're going to be okay here. But if you perceive the room, you can tell it's very boomy. And if you look at these low frequency, the reverberance here, it's really very high at 250 and 125 hertz. When you, that's the red, so that's just the rafts alone. Here, the rafts alone. When you add the rafts with the low frequency absorption, you bring the low frequency down considerably. It's a little bit high in the mid and upper frequencies. And then when you add the rafts, low frequency absorption, and the wall absorption with low frequency absorption, you start to flatten it out altogether. There is an improvement in clarity as well, and then the sound levels come down. But just before you think that having it in the walls, low frequency absorption, you can get down to this level, just a slight wake-up call when it comes to the square meterage that you have, that when you have the wall absorption with the low frequency absorption behind alone, it's still quite high. So it works well in addition to the low frequency above the rafts, but in isolation, it's not going to work so well. So if we try and look at this in graphically, actually before there's any acoustic treatment, it's way off the scale here. And if I try and bring you terms of reverberance across the frequencies and then the mid-frequency, and trying to get us into this comfort zone, the green zone, the sound strength, and then the definition of the speech clarity, D50, we can see that with no acoustic treatment, it's off the radar. And now, if I introduce the rafts and wall absorbers alone, we can see that we're coming down across the frequencies, but really not addressing anything. So it's booming here without any low frequency absorption. The sound level's controlled, but the speech clarity is not so good. And then introducing the low frequency absorption, we can see that we're getting somewhere here, but the speech clarity is still not very good. But we're starting to equalize in the low frequencies. So to conclude, it really is best to have a full ceiling and wall absorbers to balance across all the frequencies. This is something that we understand well, and it will be very inclusive for all the scenarios that are going on. So this is a particular challenge. We need to think when it's not possible, when we have exposed thermal mass, that this building is likely to behave very badly from a teaching and learning speech communication point of view. So we need to look at up to 60% of absorption. You shouldn't have a significant impact on the temperature. And then if possible, as well as the wall absorbers, if possible, have some low frequency absorption, if it's practical, behind the walls to improve that too. So that's me more or less. Thank you very much.
Thank you very much, Colin.